In this video, we'll talk about bond energy, and we'll look at using bond association energy to calculate the enthalpy of reactions. So the bond energy will be the energy required to break a bond. And relating to bond length and bond order, a smaller bond length means a higher bond energy. So shorter bonds are going to require more energy to break. So we can look at an example of some different acids formed from the halogens. And you can see here's their relative bond energy and their relative bond lengths. So this is showing that HF has the shortest bond, followed by HCl and HBr. We can notice in this trend that HF has a pretty small bond length compared to everything else. We can ask why this is the case. And this has to do with just the small atomic radius of fluorine. So remember that trend for atomic radius, it's decreasing as we go up and across the periodic table. And so as we go up this group, these are going to get smaller and smaller. And here we have two very small atoms, and so this has a pretty short bond length. We can see that this also goes with a high bond energy. And incidentally, this high bond energy means that it's a harder to break bond. And so while HCl and HBr are both strong acids, HF is actually a weak acid because of the strength of that HF bond. And remember, bond order is related to bond length, so if we have a high bond order, that would be a short bond length and a higher bond energy. So we can see this trend in these different carbon-oxygen bonds. The CO bond requires 358 kilojoules per mole to break, while the double bond requires 745, and the triple bond is 1072. One thing you'll also note from this trend is that the double bond is not exactly twice as strong as a single bond, and a triple bond isn't necessarily 3 times as strong as a single bond. Remember, these are just defined as how many electron pairs are involved in the bonding. Something else we can do with these bond energies is actually calculate the heat released or absorbed from a reaction based on the bond energy. So the delta H of the reaction tells you the heat flow for reaction done at constant pressure. If delta H is negative, that means heat is released into the surroundings. And if delta H is positive, that means heat needs to be absorbed for the reaction to occur. So to find the delta H for a reaction, you can just look at the bond enthalpy for all the bonds broken, minus the enthalpy of the bonds formed. The reason we have a minus sign here is that if we make a bond, this is the opposite process of breaking the bond. So making bonds actually releases energy. And again, we can see this in the signs. So we need energy to break bonds, requires a positive, and energy released when a bond is formed. Let's look at an example of how we do this. So say we wanted to calculate the delta H reaction for 2 hydrogens plus an oxygen going to make 2 waters. To do this, we need to know what bonds we're actually breaking, so we'd need to draw the Lewis structures for these. So H2, there's a single bond. We have 2 of them, and we have one O2, which has a double bond. And then we're going to make 2 waters, which are hydrogen, oxygen, single bonds, and we have 2 of those molecules. So to do the calculation, we're going to be breaking 2 HH bonds and 1 OO double bond. And we're going to be forming 4 OH single bonds. So to do this calculation, we'd do our bonds broken, our 2 hydrogen and our 1 oxygen, minus our bonds formed, our 4 OH bonds, to see that this reaction of hydrogen with oxygen releases 509 kilojoules per mole. You'll notice in this particular example, we actually had some extraneous information. There were no oxygen-oxygen single bonds, so we didn't use that information in this calculation. We could see an energy diagram for this. So there's our 2 species. If we were to make this reaction occur, so we followed the process of this, first we'd have to put some energy in to break up the bonds. So that would actually be a higher energy transition state where we had the hydrogen atoms and the oxygen atoms free. But when they formed the new bonds to come back together, these would release more energy than they took to break, and so would get more energy overall. So this might require an initial input, but in the net, this reaction would release energy, and that energy could kind of be used to continue this cycle. This difference between our initial condition and our final condition is this delta H that we've calculated for this reaction.